You good? Right, Gula?
Yep, we're good. We're good? Alright. Hello everybody. We're doing part 1 of the 2801-2901 seminar. The next part will be tomorrow, and it'll be me, Michael, Ronald, and Bruce Chen. And today it'll be me and Ronald, and tomorrow it'll be Ronald and Bruce. Today we're going to be covering pretty much the first half of this course. So before we start, make sure you guys sign the attendance form. That would be really good. But this is basically an overview of what we're going to be doing today. So I'll be covering the first 3 topics: introduction to probability, introduction to random variables, and common distributions. And Ronald will come in and then finish off with bivariate distributions and transformations. And yeah, I'll just point out now that although introduction to probability and like intro to random variables are obviously examinable, looking at the past papers and looking at the exam info, it doesn't seem like these first 2 are going to be like, they're not very likely to be in the exam. However, we should still cover them since they are, I guess, the fundamentals for all the other topics, and there is a chance they do come up. So yeah, we can start off with introduction to probability. So this is going to be a lot of basic stuff that you guys probably knew even before the course started. So just some definitions. An outcome is a possible result of an experiment. An example would be rolling a 1 on a 6-sided die. So when we're rolling a die, we have 6 outcomes. The sample space is the set of all the possible outcomes, so 1 to 6 in this case. And this is the notation we use for it. And an event is just a set of outcomes with an assigned probability. So an event would be like getting the score 1, and it have an assigned probability of a 6th for a 6-sided die. Probability functions. So probability itself, like P of X, is a function, and it has to satisfy 3 properties. So the first property is that all probabilities lie between 0 and 1, inclusive. The probability of a sample space is 1, and that should be pretty obvious because the sample space covers every single outcome, and you're bound to get one outcome from your experiment. And finally, the probability of any event and its complement add up to 1. So we have the probability of some event A plus the probability of A C, which is its complement, is always going to be 1. Moving on to the additive law. So for any 2 events, the probability of A or B, or A union B, is equal to the probability of A plus the probability B minus the probability of the intersection A and B. And just a bit of a side note, if A and B are mutually exclusive, well then we know that there is no intersection between them. The intersection between them is, I guess, the empty set over here, and the probability of that is getting it. The probability of getting that intersection is obviously 0. So for mutually exclusive events A and B, we just have this part of the formula, since that final term is just 0. Moving on to conditional probability. So probability of A given B is given by the probability of the intersection divided by the probability of B, I guess the event after this line. And for conditional probability questions, anytime I see the word given, I like to immediately write what we're trying to evaluate. So for example, like the probability you eat, I don't know, 5 chocolates, given you've eaten 3 chocolates. If I see that kind of sentence in the question, I'm immediately writing the probability 5 chocolates given 3 chocolates equals, and then I am using this formula in my next step. And from there, it's kind of like free game. You're going to be trying to evaluate the numerator, and then you're trying to evaluate the denominator. And yeah, that's pretty much the strat for conditional probability questions. The multiplicative law is basically saying the probability of A and B is equal to the probability of A given B times the probability of B. And this should be really clear by just looking at this conditional probability formula. We basically bring that P of B on the denominator onto the left-hand side, and we get the multiplicative law. For 3 events, it might look a bit more confusing, maybe a bit less intuitive. However, it's actually pretty straightforward if you really think about it, because to get the probability of A and B and C, well, what we can first do is try find the probability we get the event C. That's going to be P of C. And then once we've got an event C, let's think, oh, how can we get probability B as well? Well, once we're at C, we just need to multiply that by the probability of B given we're already at C. And at this point, we're now going to have collected 2 events, I guess, B and C. And similar logic applies. Now that we're at B and C, we need to multiply it by the probability of getting A, given we're already at B and C. And multiplying those 3 together would just be equal to the probability of A and B and C. You're kind of like collecting the 3 events one by one. But this formula you'd see only have very few applications. Something that doesn't really come up too often. Independence is a really important property. So 2 events are independent if and only if the probability of the intersection is equal to the product of the individual probabilities. Or you can also prove independence by proving one of these 2 equations. So the probability of A given B is equal to the probability of A, and vice versa. And just proving one of these 2 statements is enough to show that 2 events are independent. And I guess for intuition, hopefully like this formula makes sense. The probability of A given B, well, we know that if events A and B are independent, then the fact that B occurred shouldn't really affect the probability of getting A, since they're independent. Now we can look at a question from the 2018 paper. It's actually the first question, and I believe something very similar to this came up in the 2022 paper at the beginning as well. So it seems like they really like to kind of include this kind of probability question at the start of their exams. It says, let A and B be 2 events in some sample space with probability of A is greater than 0 and the probability of B is greater than 0. So we know that the probability of each event occurring is possible. Okay, because they're not 0, these events have some sort of chance that they occur. Part I says, show that if A and B are independent, they cannot be mutually exclusive. Okay, so if A and B are independent, well, we know that, I can kind of do part I, we know that P of A and B is equal to the probability of A times the probability of B. That was one of the conditions for independence. And we know that P of A is positive, we know that P of B is positive, so obviously the product is going to be positive. Hence, we've actually just shown that the 2 events cannot be mutually exclusive, because the intersection, the probability of getting the intersection, is greater than 0, whereas for mutually exclusive sets, the probability of the intersection, we know, should be 0. So we know that A and B are not mutually exclusive sets. Now with the next part, you're pretty much doing the same thing except the other way around. So now you're given that they are mutually exclusive, and you have to show that they cannot be independent. And we're pretty much going to be doing the same thing here, because if A and B are mutually exclusive, well then now we know the probability of their intersection is 0. Okay, that's just the condition for mutually exclusive sets. But we know that the probability of A and B for independent sets should be positive. Okay, and that's because the probability of getting A is strictly greater than 0, and the probability of B is getting strictly greater than 0, sorry. So we know that this cannot equal the probability of getting A times the probability of getting B. And so our condition for independence isn't true. It's not satisfied. And therefore, we've shown that if the sets are mutually exclusive, well then they can't be independent. And finally, suppose now that A and B are mutually exclusive. So find P of A given A union B in terms of P of A and B. Like I said before, for a conditional probability question, the first thing I'm always doing is writing out the formula. So in this case, P of A given A union B would be P of A and that second part, which is A union B, all on a denominator of P of the second part, the part after that vertical line, which is P of A union B. And if we think about it, the numerator is A and A union B. So I guess if you wanted to think about this visually, if we have two sets and the left set was A and the right set was B, well, A union B would be this entire region shaded. And if we want to do A intersected with that, well, we're actually only just taking set A. Okay, that would be the intersection of the two regions. So we can simplify our numerator to just be P of A, and our denominator, well, P of A union B, if A and B are mutually exclusive sets, which it tells us that they are, then using the additive law from before, we can write P of A union B as just P of A plus P of B. And we've actually finished the question because it tells us to get that term, that expression, in terms of just P of A's and P of B's, and that's what we have here. Okay? Here's a bit of a more formally written solution for this. Pairwise independence. So if we have a set of events that are pairwise independent, that means if we take every single pair, like every single subset of value 2 from this original set, well then the two sets are always independent. So if we take any AI and we take any AJ from that original set, they are independent, and hence they satisfy that independence condition. The probability of their intersection is equal to the probability, or the product of the probabilities. And I guess more generally, a set of events is independent or mutually independent if we can take any subset of this original set and it'll be every single element in that set would be independent to each other. So in other words, if we take every element from that original set, so A1 all the way up to AN, well then we have the probability of the intersection of all of them equaling just the product of all the individual probabilities. And I guess just a side note, if they tell us that a set is mutually independent, that implies pairwise independence. But the same doesn't go the other way around. If they tell us a set is pairwise independent, then we can't necessarily say that it's mutually independent. Okay? So in other words, I guess you could say mutual independence is a stronger property than pairwise independence. But just again, like, I haven't seen many questions require like any knowledge about mutual independence or pairwise independence in past exams. So yeah, again, I guess just roughly know this, but I'm still yet to see this concept applied in a question. Law of total probability is quite important, especially when it comes to Bayes' theorem. So suppose that sets A subscript I form a partition of the sample space. Well, then for any event B, we can write the probability of B is the sum of probability of B given AI times the probability of AI. And the formula looks a bit confusing, but I guess if you let B be, I guess, the number of 18-year-olds in Australia, for example. Then you could partition this set or this event into two sets. You could partition it into, say, or actually let's just say B was the set of 18-year-olds like in the world. You could partition this into the 18-year-olds in Australia and the 18-year-olds outside of Australia. And doing that, your A1, I guess in this case, would be 18-year-olds in Australia, and your other A, so A2, would be outside of Australia. And so we can break the probability of like being an 18-year-old is equal to the probability of being an 18-year-old given you're in Australia times the probability you're in Australia plus, I guess, the other term, which would be the probability you're an 18-year-old given you're outside of Australia times the probability you're outside of Australia. So it's a nice way to find the probability of an event if it's, I guess, difficult to evaluate it immediately. And it links in pretty nicely with Bayes' theorem, because Bayes' theorem is just another way of writing P of A and B, and we actually use the law of total probability in our denominator. Because the law of total probability can be used instead of, I guess, just P of B. And this numerator, which is P of B given A times P of A, if you plug that into the conditional probability formula, well, this would just be equal to the probability of A and B. And so all in all, we have the probability of A and B on the probability of B, which we know is the formula for P of A given B. So again, it's just a nice way of rewriting P of A given B. And anytime you see a question that's on like diseases and like false positives and false negatives, you're pretty much always going to be using Bayes' theorem. That's like the one question that is a bit of a giveaway that you're going to be using Bayes' theorem. We'll move on to the next topic, which is introduction to random variables. And we'll just start off by defining them. So, sure you all know this already, but a random variable is a variable whose value depends on the outcomes of a random experiment. So for example, the random variable x can represent the score you get when you roll a die. And we often denote them by capital letters. Now, cumulative distribution functions are like probably the most important functions in statistics because they like uniquely define a distribution. And it's denoted by capital F, and it basically tells us the probability that our random variable is less than or equal to something, in this case x. So it has two properties. The probability that your random variable is going to be greater than x, well, if we think about how complements work, this is going to be equal to 1 minus the probability your random variable is less than or equal to x, and that probability is just your CDF. And the other property, for any x is less than y, the probability that your random variable is like sandwiched between x and y, is going to be the CDF evaluated at y minus the CDF evaluated at x. And this is something that's really clear when you like draw out a number line. So say this was our x and this was our y. The probability that your random variable is sandwiched between these two values on the number line is going to be the probability it lies in this region minus the probability it lies in this region. I really wish I had different colors, but I'm not too sure how to do that on this program. If you kind of just see that like visually, this region I guess gets like cut off and you're just left with the region in between x and y. Now some other properties, I guess more formal properties. The limit as x goes to negative infinity of f of x is going to be equal to 0. And that's because, like, hypothetically, there exists no real numbers to the left of negative infinity, I guess. So, obviously the probability you're going to get a value smaller than negative infinity will be 0. And the same goes on the other side. Pretty much every real value is going to be less than infinity. So the probability we get a score less than infinity is obviously going to be 1. F is also non-decreasing for all x, i.e. if x is less than or equal to y, well then f of x is less than or equal to f of y. And this should make sense because if y is bigger than x, well then you're allowing your random variable to take on a greater range of values. And so you'd expect your probability of getting a score less than or equal to y to be greater than or equal to the probability of getting a score less than or equal to x. F is also right continuous, which I haven't seen be applied in too many questions, but it means that the limit as t goes to x plus of f of t is equal to f of x. So in other words, f of x plus, so the value just very slightly to the right of x, is going to be the same as f of x. But just note, the same doesn't apply for like the left continuity. So f of x minus is not necessarily equal to f of x. That's why we just say f is right continuous, not left continuous as well. Onto like the types of random variables. So we have two types. We have discrete and random. So a random variable is discrete if it can take a countable number of values. Now, obviously something like rolling a die is going to be discrete because there's 6 different values. But a lot of students make this common mistake. So if your random variable can take the values 1, 2, 3, and so on, all the way up to infinity, so like there is no upper bound to the value it can take, a lot of students say that this is actually a continuous random variable because there are infinite outcomes it can take. However, this is still classified as discrete, and the reason why is because this sequence of numbers 1, 2, 3 all the way up to infinity is countable. In other words, we can actually order these values. So like 2 is greater than 1, and then 3 is greater than 2, 4 is greater than 3, and so on. And so even though that there is infinite number of values the random variable can take, we still say this is discrete. The probability mass function, more commonly referred to as probability density function, or the PDF, is given by like little f, that's the notation we use. And it's basically, for a discrete random variable, it's basically spitting out the probability that our random variable is equal to x in this case. And it's related to the CDF by this property. So capital F of x is going to be the sum of all the individual probabilities of getting a score less than or equal to x. Okay, so say x could take on the values 0, 1, 2, 3, 4, if we wanted to find the CDF of the random variable at 2, well, this would just be the probability that the score is 2 plus the probability the score is 1 plus the probability the score is 0, because 2, 1, and 0 are the 3 scores that are less than or equal to 2. Continuous random variables, they're, I guess, more straightforward to identify. Basically can take a continuum of values, and essentially a random variable is continuous when the score, or like the possible outcomes, is a real number, any real number between, I guess, between two values. Okay? So for example, x is any real number between 0 and 1. That would be a continuous random variable. And with continuous random variables, we're not concerned with like the probability of getting a certain score. For example, the probability your random variable is exactly 2, because with continuous random variables, we know that that probability would be equal to 0. So say x is our random variable, that's continuous. We know that the probability that it's strictly equal to some value, some constant, is going to be 0. And that's just, I guess, a property of continuous random variables. Rather, we're more concerned with, what's the probability your random variable lies between two values? Okay, we care more about intervals as opposed to discrete single values. And hence, we have a formula for this. The probability that your random variable lies between a and b is just the integral of the PDF between a and b. Okay? And with the CDF, capital F of x is going to be the integral from negative infinity to x, because negative infinity to x will cover all the values less than or equal to x on the number line. And again, we're just integrating the PDF. Just know that negative infinity is really like a standalone for the smallest value the random variable can take. For example, if our random variable can take any value from 0 to 6, for example, then this lower bound wouldn't be negative infinity, it would be 0 in this case, because that's the smallest score we can possibly get. But your upper bound will always be x. And a really important property, we can derive the PDF from the CDF simply by just differentiating with respect to x. And this is quite a straightforward property, because it's actually a direct result from the fundamental theorem of calculus. If you differentiate this integral on the right hand side, all you pretty much need to do is chuck this x into the PDF and replace it for t. So you're just left with f capital X of little x, which is what we have on the right hand side. And also by the fundamental theorem of calculus, if we had something like capital F of, let's say, 2x, for example, well, we know that this would be equal to the integral from negative infinity to 2x this time of our PDF. Sorry, I should be using t. And now when we differentiate both sides with respect to x, we get the derivative of that CDF is going to be equal to the derivative of this upper bound. So before, when our upper bound was x, the derivative was 1, so we didn't really have to worry about it. But now, because our upper bound is 2x, we multiply by 2, that's what the chain rule tells us, and then we sub in the 2x in place for t, just like we subbed in the x in place for t here, and we get 2f of 2x. But this is a property that would probably be assessed in more challenging questions, and actually a question that we'll be looking at shortly. Expectations, probably the most important statistic, I guess, in all of statistics. It's denoted by E of x, but you could also call it mu. And it's essentially the mean of a random variable. For discrete random variables, we're going to be using sigma, like we always use for discrete random variables. And it's going to be the sum of all of the possible scores, x, times the probability of getting that score. Okay, so for a dice, our possible scores are 1 to 6, and the probabilities assigned to those scores are all a sixth. So you can think of the E of x calculation as the first score, which is 1 times a sixth, plus the second score times a sixth, all the way up to that last score, which is 6 times a sixth. For continuous random variables, we're going to be integrating across all possible values. Since we're dealing with real numbers, covering from negative infinity to infinity should cover all the real numbers. And just like in discrete, we did the score times the probability of getting that score, we do something similar. We do the score times the PDF of that score. Now, when we're not trying to find E of x, when we're trying to find E of some function of x, well then it's the same thing as before, but we are now replacing these scores, x, in the calculations with our new function, g of x. And you'll probably would have used this a lot already when you're trying to find like E of x squared for variance calculations. In this case, your g of x is, well, simply just x squared. And so you sub in your x squared into both of these, depending if you're dealing with a discrete or a continuous random variable. Just some properties of expectations. The expectation of a constant is just the constant. Pretty straightforward. Expectations are linear. So if we wanted to evaluate the expectation of ax plus b, where a and b are constants, well, we can write that as a times the expectation of x plus b. And the same goes with like dealing with multi-random variables. If we wanted to find the expectation of ax plus by, we can write it as a e of x plus b e of y. The way I like to think of it is, if I'm trying to find an expectation of some expression, I'm pretty much going left to right, and I'm picking out the constants from the random variables. So I'm looking at this ax term, I see an a is a constant, so I take it out of the expectation, and I've hit a random variable, so I can rewrite this x as e of x. And then I keep moving on, I see a b, that's a constant, so I'm not putting that in any expectation. Same goes with this second case. Pretty much use like the random variables as roadblocks, and I put them in the expectation. And if x and y are independent, well then we have this nice property. Expectation of the product is the product of the expectations. However, this can only be used if we know they're independent. So either they'll have to tell us they're independent, or we'll have to prove that the two random variables are independent. And that's something that would probably be covered, in today's lecture, towards the end. Variance. So variance, we have two formulas for it. We have the expectation of x minus e of x all squared, or e of x squared minus the expectation of x all squared. And to evaluate variance, we're probably always going to be using the second formula. I don't really see a case where you would use the first formula over it. And we already know how to compute e of x squared using that formula from above, where your g of x is x squared. And to evaluate standard deviation, we simply just square root the variance, because that's the relationship between those two statistics. Properties. So properties of variance is a bit different. If we wanted to find the variance of ax plus b, basically, whenever you see a constant in front of a random variable, you can take it out and square it, just like we have here. The a inside the variance becomes an a squared. We hit that random variable roadblock, so we write this as var x, and we move on. We hit a constant b. It's important to note that the variance of a constant is 0. Okay, so var of b just becomes 0. So we don't include it. Another way of writing variance is the covariance between x and x. Not too important if you already know what the covariance formula is, but this will probably come up in tomorrow's lecture. More importantly, the variance of the sum of two random variables is the sum of the individual variances, but we also have this crossover term, which is 2 times the covariance of x and y. And so whenever you want to find the variance of two random variables summed together, you're going to have to evaluate this covariance term first. Just note that if x and y are independent, well then this covariance term is actually just 0. So when x and y are independent, we can write var of x plus y is just simply var of x plus var of y. Okay, let's look at a expectation and variance question. So we have this PDF, it's a piecewise function. It's pretty much telling us that x can only take on values between -1 and 0. Otherwise, there is 0 chance it can take that value, so we don't really have to worry about it. Part I says, find k such that the above function is a probability density function. So we should know that to be a valid PDF, we need the total area under the curve to equal 1, because the area under a continuous density function curve represents the probability, and so we want total area to be equal to 1. So I can do that here. We have the integral of from -1 to 0, because that's the interval our x can take, of that PDF, which is k x squared plus 2x plus 1. We can write that as just x plus 1 all squared dx. We know that this has to equal 1. I can take the k outside of this integral because I know it's a constant, and if we integrate x plus 1 squared, well, that's simply just that's simply just a third x plus 1 cubed. Evaluated between -1 and 0. And we have k on 3, and then inside these square brackets, if we sub in 0, we get 1 cubed, and if we sub in -1, we get 0 cubed. So all in all, we should get 1 cubed minus 0 cubed. That's equal to 1. We know these brackets evaluate to 1 itself, so we don't really have to worry about this term. All we do is bring this 3 across to the other side, and we get k equals 3. And so k needs to equal 3 for that PDF to be valid. I might just add a page here if I can. Insert page. Okay. Cool. Now it's asking us to compute the expected value of x. So now we know exactly what the PDF is. It shouldn't be too difficult to evaluate the expectation, because e of x should be the integral of all the possible values, which we know are between -1 and 0, of x times the PDF. And this is going to be equal to integral from -1 to 0. We know that f of x is 3 times x plus 1 squared. So I could probably already take the 3 out. And I'm left with x times x squared plus 2x plus 1. It's going to be equal to, easiest way to do this would just be expand that integrand to get x cubed plus 2x squared plus x. And now we can evaluate that integral to be 1/4 x to the 4 plus 2/3 x cubed plus 1/2 x squared, evaluated from -1 to 0. Now we know when we sub 0 in, all of these terms are going to be 0. So that's already going to be 0, minus, when we sub in -1, this first term, 1/4 times x to the 4, would just be 1/4. This next term, 2/3 times x cubed, would be minus 2/3. And this next term, 1/2 x squared, should just be plus 1/2. And this is going to be equal to, we can kind of remove this 0, take the negative out. It's going to be -3 times this expression, which should be, this is going to be 3/4 when we add the 1/4 with the 1/2, minus 2/3, which should be equal to, if we evaluate this fraction, should be 9/12 minus 8/12. So that's 1/12 times by -3 should be -1/4. And so that's our expectation. And we should ask ourselves, does it make sense that we got a negative expectation? Well, if we look back to the PDF, x can only take values between -1 and 0. And so we expect it to be a value between -1 and 0, and -1/4 is. So I guess that's a bit of like a sanity check to make sure our answer isn't wrong off the bat. And to compute the variance of x, I might just add one more page. Okay. To find var of x, we need to first compute e of x squared. E of x squared is going to be the integral from -1 to 0. And now it's not x times the PDF, it's x squared times the PDF. Now the PDF has that k factor at the front, which we know is 3. So we can take the 3 out the front already. And we just need to multiply this part by x squared. And that would just be x to the 4 plus 2x cubed plus x squared. And we're going to evaluate that. It's going to be 3 times 1/5 x to the 5 plus 1/2 x to the 4 plus 1/3 x cubed. Evaluated between -1 and 0. Again, when we sub in 0, this expression is going to be equal to 0. Minus, when we sub in -1, we're going to get -1/5 plus 1/2 minus 1/3, which is going to be -3. Again, we don't have to worry about the 0. -3 times this expression, which should be a half minus 8 on 15, I believe. And that is going to be equal to, obviously I'd use a calculator at this point, but 8 on 15 we can write as 16 on 30. So it should be negative 1 on 30, I believe. And this is going to be equal to a tenth. And we have a positive number now, so again, let's just give a quick sanity check. It makes sense because the expectation of x squared should be a positive number. We know that x squared, no matter what value of x is, should be a positive number in the real world. So that's fine. And now that we have e of x squared, and we also have e of x from the previous part, we're ready to compute var of x, because var of x is e of x squared minus e of x all squared, which is 1/10 minus, we said the expected value was negative a quarter, so minus negative a quarter all squared, which is a tenth minus a 16th, which is going to be equal to, what's that, 3 on 80, I believe. Yeah, 3 on 80. And var is always going to be a positive number. So the fact we got a positive number is a reassuring thing. And that's the end of that question. The next question I have is a bit more complicated. It was actually one of the last questions in the 2008 paper. So I might add a page here. Okay, now it basically tells us the standard normal distribution and the chi-squared distribution, or chi-squared, with degree of freedom nu. These two you will cover more formally tomorrow. And it also tells you the gamma function of a half is root pi. Now it looks complicated and it looks like something that's probably not in these topics, but the working for this question is all in this topic, so nothing to stress. Part A asks us use the PDF of that normal distribution to show that e of z is 0. That should be pretty straightforward. Obviously we know the expected value is 0 because it is a normal distribution with mean 0, so nothing should come as a surprise there. But using our formula, we integrate between all the possible values, and for a normal distribution we know that all the possible values is, I guess, all the real values, and we're going to be doing our score, which in this case is little z, times the PDF. And in this case, they give us the PDF. They tell us it's 1 on root 2 pi, but I'm multiplying that by z over here. So it's going to be z on root 2 pi e to the negative z squared on 2. And this looks a bit horrific to compute. Still actually pretty straightforward because you can kind of use like either U sub or reverse chain rule to get it. However, it's important to note that this integrand is odd. Hopefully you guys can see that. If we replace z with minus z, we actually get the negative of this integrand, hence showing that this integrand is odd. And because we have symmetry in these limits of integration from negative infinity to infinity, whenever we integrate an odd function with that symmetry, the solution is actually just 0. And you'd probably have to include a reason. So because the integrand, which is your function inside the integral, is odd. So that's part A. We've showed that e of z is 0. Part B, let y equals z squared. Show that we have this. So in terms of the CDFs, so that was part A. Part B, sorry, let me just check how I'm going for time. Okay, should probably go a bit faster. But part B, we have f of y is going to be equal to, well, we know that the CDF of y is going to be, it's going to be equal to the probability that our random variable, which is capital Y here, is less than or equal to little y. But we know that big Y is just big Z squared. And the probability that Z squared is less than or equal to Y is actually going to be equal to the probability that Z lies between negative root Y and root Y. Right? Because if Z takes any values between these two, then when we square it, we're going to be less than or equal to Y. And again, we have like this sandwich idea where the random variable is sandwiched between two constants. We can write that as the CDF of Z being less than or equal to root Y, the bigger bound, minus the CDF for the smaller bound, which is that. And I believe, yep, that's all we had to show. So that's the end of part B. And finally it says, hence find the density function of y and identify the name of this distribution. Now I might have to skip this part, but I will include this solution in the slides, or I might come back to it if we have time at the end. But the way you do that is you just differentiate both sides of this expression that you just proved with respect to y. Okay, that's the first step, and from there it should be pretty clear. And they've given you the chi-square distribution, so obviously there will be some relationship between what you got and this chi-square distribution. Otherwise, like, there's no reason they included this at all. And the relationship should be pretty clear after one or two lines. But I'll get back to that at the end, and I'll include the solution in the slides when we upload them, just because we're short on time. Move on to moment generating functions. This is a really important concept, something that will definitely be assessed. And it's basically a function that is equal to the expectation of e to the tx, where t is some constant. And it's a really weird expression, but it's really useful because it pretty much spits out the moments of a distribution. So we use the MGF to find moments of a distribution and also to identify distributions, since moment generating functions are unique to a distribution. So in other words, if two random variables have the same MGF, have the same moment generating function, then we can claim that they have the same distribution. Now, I said we could use the MGF to compute the moments. The moments look something of the form of this, e x to the r, where r is a positive integer. We're familiar with e of x. We're familiar with e of x squared. To compute higher moments, using the MGF is definitely advised. And the way we compute it, well, to get the rth moment, we have to first differentiate the moment generating function with respect to whatever your variable inside it is. It's usually t or u. You differentiate it with respect to that variable r times, and once you've gotten that derivative, you just let t be 0, or you take the limit as t goes to 0, and that'll be equal to your rth moment. So we can look at a quick question here. Let x be a random variable. May have done random variable twice. With PDF function defined as this. Now, hopefully you guys know that this follows a uniform distribution from A to B. Hopefully that looks pretty familiar. find the moment generating function. Now, the moment generating function, I'll use the variable t here, you can use u as well, is going to be equal to the expectation of e to the tx. And thinking back to a previous slide where this was kind of like our g of x, we know that this is going to be equal to the integral. We know that all the possible scores lie between a and b, so those are our limits of integration, and our function g of x is going to be e to the tx here. And we also have to multiply it by the PDF, of course, which is 1 on b minus a dx. Now, 1 on b minus a is a constant, so I can take that out of the integral, and all I need to do is integrate e to the tx. That's pretty easy because e to the tx becomes 1 on t, e to the tx, and I'm just evaluating that between a and b, and the t is, you can think of it as a constant in this case, so I can put that t, I can join that t with the b minus a on the denominator. And so I'm just evaluating this e to the tx between a and b. Now when I sub in the b, I get e to the bx minus, and then when I sub in the a, I get e to the ax. And that's our moment generating function for a uniform distribution. And you can actually like check this or cross-check this with the reference sheet that they're going to give us for the exam. This should be the moment generating function for that uniform distribution. Useful inequalities. Probability that x is greater than or equal to a is less than or equal to the expectation divided by a. It's just an inequality that you should probably memorize. There's not too much intuition behind it. The proof's a bit bland and long. But yeah, I guess it's an inequality to memorize. And also Chebyshev's second inequality, which is this one. This one's saying pretty much the distance between your random variable and the mean of it. The probability that that distance is greater than or equal to k sigma, so where sigma is your standard deviation, is less than or equal to 1 on k squared. For those familiar with z-score, this is pretty much saying the probability that your z-score is greater than or equal to k is less than or equal to 1 on k squared. Maybe that's a bit more intuitive or nicer to think about. And these inequalities don't really have much application. I found one application from like the 2801 notes, so not even an exam paper. The question goes, a factory produces 500 machines a day on average. It is subject to a variance of 100. Let x be the amount of machines produced tomorrow. Find a lower bound for the probability that between 400 to 600 machines are produced tomorrow. So it's really this hint of finding a lower bound that kind of suggests we should use an inequality. And because we want to find the probability that it's between 400 to 600 and the mean is 500, we can think about it as finding the probability that your distance from 500 is less than 100. That's pretty much saying that your random variable has to be between 400 to 600. So we're trying to find this probability, and it looks awfully familiar to Chebyshev's second inequality, which hopefully you guys will have memorized for the final. Mu is our 500 in this case. Sigma, well, sigma is going to be 10. And that's because our variance is 100. So square rooting that gives us a sigma of 10. And so we can write this 100 as 10 times 10, where the first 10 is our k, and the second 10 is our sigma. Okay, and it tells us that this probability is going to be equal, or less than or equal to 1 on k squared, where the k is 10. So the probability of this is going to be less than or equal to 1 on k squared, which would be 1 on 10 squared, which is 1 on 100. And so a lower bound for our probability initially is going to be 1 minus 100th. It's going to be 99 on 100. Sorry if that was a bit rushed. But yeah, hopefully it's not too complicated. Jensen's inequality. This is another one that you should just have memorized. I'm not sure if it applies in 2801, but I think it can be assessed in 2901. You just have to memorize this. I haven't seen any application of this in previous years. Just know that in this inequality, h has to be a convex function. That's the only condition. And if h is a convex function, you can apply this inequality whenever you want. Still yet to see a question with that inequality. And finally, just to rush through these, common distributions. So you're going to be getting a reference sheet in your final, so it's all right to, I guess, forget about them. But we're going to go more through like what they intuitively represent. So for discrete distributions, we have Bernoulli, and the parameter is p, and it's basically a single trial where a success has probability p and a failure has probability 1 minus p, or usually represented by q. Binomial is the same thing, but it's not a single trial, it's actually n trials, and that's our new parameter, n. And it models number of successes out of those n trials. Geometric distribution. So this basically models the number of trials it will take until you get your first success. For example, like flipping a coin, we know that there's 2 outcomes each toss, head or a tail. You can use a geometric distribution to model how many tosses will it take until you get your first head, for example. Negative binomial, I'm pretty sure it's said in the spec, don't worry about it. So I wouldn't worry about negative binomial, even though the formulas are given on the reference sheet. Poisson, so there's one distribution, lambda. Poisson is pretty useful to know off the top of your head that mu and your variance, both of these are equal to lambda. But that's on the formula sheet. And it basically models like the number of occurrences of a random event at a rate of lambda on average. So if you know that like there are 3 people coming to a pizza shop every hour, your lambda would be equal to 3, and your Poisson 3 would model the number of people coming to the shop at that hour. And continuous distributions, so uniform, very straightforward. Basically, your random variable can lie anywhere between A and B inclusive, and it has like equal probability, I guess, of taking any one of those values. Exponential, so this one's often used to model the time it takes for an event to occur. So usually associated with like waiting times, I guess. Gamma distribution, not too sure what the application is for this one, but just know that when you sum alpha independent exponential random variables with parameter beta, you can combine that into a single random variable that follows a gamma alpha beta distribution. So just know that it's when you sum alpha independent exponential variables. And I believe, yeah, we have normal and beta left. So normal, you'll be going through in a lot more detail tomorrow, but it's just a bell curve distribution and it's symmetric about its mean, mu. Standard normal distribution is the one we often represent with the capital Z. It's just a standardized normal distribution where the mean is 0 and the standard deviation and variance are both 1. And to get a standard normal distribution, we apply this transformation, but again, this is going to be covered tomorrow, I believe, when you go through central limit theorems. Finally, a beta distribution. I have zero knowledge of the application of this distribution, but just know that the formulas, like for the mean, variance, and the PDF, are on the formula sheet, and they can be assessed. And the last thing, like it says in the spec, really, is just make sure you're familiar with the R commands, because they can provide them in the exam, and you have to know what each command does. So yeah, basically these are the main four. R isn't really necessary for the exam, neither is D, I would say. It's really just these two, P and Q. So P gives the CDF value at some probability, I guess. Sorry, not probability. It gives the CDF value at some outcome, and Q gives you like the quantile function. So you input a probability for Q, and it gives you the value that corresponds to that quantile, essentially. But I'd recommend having a play around with these two in R just before the exam starts, I guess, just to be familiar with them. And here's a question, I think it's the last thing. It's a question from a 2020 paper. So suppose that the probability of hitting a target is 1/5 and 10 arrows are independently fired. Because they're independently fired, we're dealing with 10 trials, I guess, and in each trial there are two outcomes, right? It hits the target with probability of 1/5, or it doesn't hit the target with probability 4/5. It's clear we're dealing with a binomial distribution here. In fact, we're going to be dealing with a binomial distribution where our first parameter is the number of trials, that's 10, and our second parameter is the probability of success. In this case, it would be hitting the target, and that would be 1/5. So this is the random variable we're dealing with. Part A, what is the probability that the target is being hit at least twice? Well, this phrase "at least" suggests we should be thinking about the complement. And so the probability that we hit the target at least twice would be 1 minus the probability we hit the target less than 2 times. Okay? And in an exam, maybe not for this question, because this question is pretty simple to calculate, like using a calculator, but in an exam it'll provide like these commands, and looking at this first command, the probability that it's less than or equal to 1 for a binomial distribution with mean 10 and probability of 1/5 is 0.3758, so on. So we can sub that into our f of x of 1. And in the next question, what is the conditional probability that the target is hit at least twice, given that it is hit at least once? Well, I'm immediately writing P of x is greater than or equal to 2, given x is greater than or equal to 1, because that's just like writing the question, or writing what we're trying to find in a mathematical expression. And then instantly I'm using our conditional probability formula. I've used a comma here, but this is the same thing as like the intersection. And notice that this numerator, P of x is greater than or equal to 2, and x is greater than or equal to 1, we can simplify that to just x is greater than or equal to 2. Because we know that if x satisfies this condition, it must also therefore be greater than or equal to 1 and satisfy the other condition. So we're just trying to evaluate x is greater than or equal to 2 on x is greater than or equal to 1. We know the probability of x is greater than or equal to 2 because that was our answer in part A. All we got to do is find this denominator, but again, using complements, we can write that as 1 minus the probability of getting like 0 successes, I guess, or f of 0, where f is the CDF, and again, we're provided with that value. That would be this bottom value here, and we know that's 0.107 something, so our denominator is going to be 1 minus that. It's going to be 0.89, so on. And we plug it into our calculator and we are done. Cool, sorry if that was a bit rushed, but you can always look back and I guess go through it at a slower pace. I'll make sure to include the solution for that last part of that distribution question, and I'll pass it on to Ronald to start looking at bivariate distributions. So thanks everyone.
Hello? Right, it seems everything's working now. Welcome, welcome. Thank you to Michael for doing the first part. I'll be handling the second part, which is going to be bivariate distributions and then transformations. I think it'll be very helpful if we first just look at what a question might look like. So first of all, bivariate, it means two variables, specifically random variables. You'll see that we see this in the question. We have an x and a y. Both of them are random variables. And then we have something called a joint density function. You might be wondering, hey, what exactly is that? Well, here's an example of a joint density function. You might have heard of a PDF, a probability density function, which is essentially this same function, but in one dimension. So it might look something like this, where it's maybe a bar graph, and for some x value, they give you a probability, right? Well, the difference between a normal one-dimension distribution and a bivariate distribution is that instead here we get two variables, right? Usually an x and a y, and then these two inputs are mapped to a specific output, and this output is our probability. So instead of getting a probability from maybe just one x, we get an x and a y, and these two give us a probability where the probability is the chance that both x is equal to the value, let's say 0, and y is equal to value, let's say -1 in this case, right? So the way we might look at it is we have x equals 0, y equals -1. So if we look at the specific related column, which is right here, this would represent the probability that both of these happen together. And so this is a discrete example, right? Where x and y are discrete variables, but if it was continuous, it would look closer to a curve. So what is a joint density function? It's just a function f where it takes in an x and a y from two random variables and outputs a probability. So you might see that these are pretty similar in terms of properties to what we had in one dimension, right? So the first property is that every single probability is non-negative. And of course we know that's true with all probabilities, so that's not too different. The next one says the integral across r squared is equal to 1. What does that mean? Well, in the context of a joint density function, it just means if we integrate across this entire plane, which means add up every single probability available, it will sum up to 1, right? So that's all it means. It means all the probabilities combined is 1. And that's pretty much the same as before. And then what it says here is the probability of a given region is just the integral of the region, right? So let's say that this is kind of a top-down view of our x and our y. If we wanted to find the probability that our x and y are in this region, then what we would do is we would just integrate throughout this region, right? And this integral just says add up every single probability in this area. And that's essentially how we find the probability that we get something in the area. Right? Pretty simple. Shouldn't be too bad. So now that we know what a joint density function is, you might see, hey, we have fxy, and it's equal to 1 on 100 times e to the power of minus x plus y over 10. Now we go to the first part. We see, hey, we want to determine the marginal density. I think you already have a bit of a clue what a marginal density is from what they expect us to calculate, which is f of y. So what a marginal density is just the PDF of x or y, and we get this from integrating our joint density function. But what is this integral doing? Well, let's go back to our example. Let's say that we wanted to find the probability that maybe x was equal to 2. How do we do that? Well, the way we do that is we look at every single scenario, right? We know that x can be equal to 2 if, for example, y is equal to minus 2. Maybe y is equal to minus 1.5, and so on. And so what you do is you look at every single possibility where x is equal to 2 in this strip, and then we add them together, right? Because that would get you the probability that x is equal to 2, since in this case, we don't really care about what the y value is, right? So just for every single possible y value, we add up all of the probabilities when x is equal to 2, and that gets us the probability f of x 2. And of course, this isn't unique to 2, right? We can do this for 0 or 1 or half and any other x value. So what we see here is to find, for a given x value, the probability, we just add up. So that's what the integral is. It's adding up every single y value from minus infinity to infinity. Right? It's just adding up everything in that strip, which is every single possibility where x is equal to this x right here. And it's pretty much the same thing for discrete random variables, where instead of integrating, you just add them up, since obviously there's a finite amount and you don't require integration. So that's what the marginal density is. It's just getting the PDF of x or PDF of y independently from the joint density function. So now that we know that we just want to find fy of y, and we know that what that means is we want to find the probability for a given y, and the way we do this is if we want to find, for example, y equals 2, we just add up every single probability in this strip right here, and except this strip is going along the x-axis, right? It's parallel to the x-axis, so instead we, for the y, integrate with respect to x. So we're summing up every probability along the x-axis for a given y. And of course, we know that it's defined for us that x is actually greater than 0, which means that our region to integrate by is actually 0 to infinity. And we just integrate our joint density function. We get 1 on 100 times e to the minus x plus y over 10. But then we realize that since it's with respect to x, our y right here is a constant. So we kind of just ignore it. We just say, hey, the coefficient of the x is minus 1 on 10. So we divide by that coefficient, and we get this. We sub in our x equals 0, x equals infinity. I think it'd be pretty useful to say x equals infinity, x equals 0, because there are two variables in this case. Then we just sub the variables in and simplify, which gets us 1 on 10 times e to the minus y on 10. And this is our marginal density or probability density function for y. So now that we have the first part down, we might say, hey, what exactly is a conditional density? Well, a conditional density is just the probability density if we're given that our y is already equal to the value of y. So what does this formula mean for us? It just has the joint density function over the marginal density function. Why is that? Well, the reason is because if we want to, for example, have our f of maybe x given y, where we have an x which is 2, given that y is equal to 2, what we see is that since we're given that y is equal to 2, we know that every choice that we have is guaranteed to be on this line, right? Since any other horizontal line would mean that y is not equal to 2. So every event is now occurring on this line, y equals equal to 2. That's why we need, for the case where x is equal to 2, we can only look at this square right here, right? This square. So what is the value of this square in terms of probability? Well, it's just f of xy to 2, right? And then what's the total probability? The total probability is just the probability that y is equal to 2. And that's essentially where the formula comes from. So we have the joint density function of x and y over the the margin density of y. And that represents the probability of x given a specific y. Here is some conditional expectation and conditional variance. Essentially, what's the expected value of x given that y is given, right? So what is the expected value of a function of x given that y is already set? Well, instead of multiplying by our usual density function, we just multiply by our conditional density function, since this represents our new, PDF based on the fact that capital Y is equal to Y. So essentially it's just replace f of xx with f of xy, xy. And then of course we have the variance formula. It's just e of x squared minus e of x squared, except in this case we have the fact that y is already set. Hopefully that makes sense. Now we want to find the conditional density function, which is f of y given a value of x. So the first thing we know is that from our slides, this is going to be some f of xy joint, and then we're already given what our x is, so we divide by the marginal density for x. Since we haven't calculated that yet, we calculate it right here. We can follow the same steps from part 1 to get it. So for here, I just given it to you, but in an exam, of course, you have to calculate it. So we know that f of y given x is given by the joint over the marginal of x. So that's this function right here over this function right here. The coefficients cancel to get 1 on 10, and then we can use indice laws to simplify these two terms, and that gets us and minus x plus y over 10 plus x on 10, and we know that these x on 10s cancel, and in the end we get a 1 on 10 times e to the minus y on 10. So in our third part, this is actually a very common question for these kinds of joint density function questions, which is x and y independent? Well, what does it mean for two things to be independent? That means they don't affect each other, right? So this is there are a couple ways we can prove that it's independent. The first way is if we show that the joint density function is actually just f of x times f of y. And the reason this works is because if they are independent, then the probability that x equals x and also y equals, just gonna rub this out a bit, x equals x and y equals y, the probability that both of these happen together would just be the probability that x is equal to x multiplied by the probability that y is equal to y, right? And this is kind of the same intuition here. Essentially, the probability that both x and y happen is given by the probability of x happening times the probability of y happening. This is only true for every x and y value if it's independent. So remember that this has to be true for every single x and y value. Just because you find one value doesn't mean it's independent. But if you find one counterexample, then that's a way to prove that they are not independent, right? Because this has to be true for every single value. And the last part is using conditional PDFs. So we have the function if x, f of x given y, and that's equal to f of x. Well, obviously, this would be true if it would be independent. What this says is, no matter what y value you choose, our f of x is going to be the same. Which means f of x is the same regardless of what y is, which means that they are independent, right? And the same is true with the other equation. It just says for any x value, the PDF of y will stay the same. And so this is a very easy way that we can show two random variables are independent. So, are x and y independent? We have three methods, and all three methods are valid, but I think this third method right here is much simpler. Why is that? Well, the question previously asked us to find out f of y given x, and also f of y. So we can use this. We know what f of y is. We know what f of y given x is. We know that they're equal. So we can say, yes, x and y are independent. So here's the fourth part, which is calculating the probability of x plus y, which is less than 1. If you remember from before, the way we calculate probability is by finding out the area, right? And then we integrate across the area. So generally, the first thing I do is I look at the domain and range, right? So we know that the domain is set by the fact that x has to be greater than 0, y has to be greater than 0. Then we look at the probability. In this case, it's x plus y is less than 1, which means we know that our value of x plus our value of y has to be less than 1. And we can transform this into a y which is less than 1 minus x, right? And if we graph this, what we get is we have a line right here, which is 1 minus x. We have our x-axis and our y-axis. And the region that fits every single criteria here is this one, where this is 1, 1, 0. And so if we just integrate this triangle, then we get the probability that we have up here. And of course, we can do this for a lot of other probabilities. You know, for example, if we have the probability x squared plus y squared is less than 1, then that's saying integrate the area under this quarter circle right here. So I think this is a pretty versatile trick where you take the inequality inside the probability and then you turn it into a function, you graph it out and find out what area do I need to integrate. So these are the traits. It's just x is greater than 0, y is greater than 0, x plus y is less than 1. So this is what we've done. We've taken our area right here, and what we've done is we've said, hey, our y values range all the way from 0 to this line right here, right? So that's why our bounds for dy is 0 to 1 minus x, since we never go past 1 minus x. And then our x values are ranging from 0 to 1. So we integrate with respect to dx from 0 to 1. And then we just do the integral, right? It's a normal integral. We say it's dy, so x is a constant. So we look at minus 1 on 10 as our coefficient. We divide by the coefficient and so on. We get this once we integrate. We sub in our 0 and 1 minus x. We get this. We see that e to the minus 1 on 10 is a constant, so we add an x. This is an exponential, so we divide by the coefficient. We sub in the numbers, and in the end we get this as our probability. Hopefully that was not too bad. So now here's an example of a discrete bivariate. This comes across as a table where we have a bunch of possible x values, 0, 1, 2, a bunch of possible y values, 0, 1, 2, and then the probabilities, right? So if we got x equals 1 and y equals 2, then that would be the probability of 0.09. Our first goal is to find the marginal distribution, which, as we remember, is just the f of x function. So what do we know? Let's say we wanted to find the f of x when x is equal to 0. We know that we don't really care about what y values there are, so we just add every case where x is equal to 0. So that's 0.15, 0.12, and 0.106, and that gives us 0.33. And we can keep doing this for the rest of the rows, and that would give us row 1 to be summed up to 0.33, row 2 to be summed up to 0.3, and row 3 to be summed up to 0.37. Now we have the test, is x and y independent? Well, how do we find this out? An easy way for discrete is just finding any value where if you multiply the probabilities together, they are not equal to the probability on the table. So what we can do is we can find our marginal zero value for y, right? We just add up everything in the column, and that gets us the probability that y is equal to 0, which is 0.3. Now, we know that the probability to get a 0, 0 is 0.15 from the table, but then we know that f of x0 is actually equal to 0.33, and f of y0 is 0.3. If we multiply them, we get 0.099. This is obviously not 0.15, so we can say, no, this is not independent. So, here's the final question for this part. What is the covariance between x and y? The first thing is, what is covariance? Well, covariance specifically is just a pretty easy formula. It's the expected value of x times y minus e of x times e of y. What is covariance actually? Well, what covariance says is, if the covariance is large, then that means as x grows larger, y grows larger. If the covariance of x and y are small, then it says if x grows larger, then y grows smaller. Or if y grows larger, then x grows smaller. And if x and y have a covariance of 0, that means no matter how x moves, it doesn't actually affect how y moves, and vice versa. So this, if x and y are independent, that means they don't affect each other, then covariance is 0, obviously. We also have the fact that the covariance of x and y and x are the same, and covariance is linear. So, what is the covariance between x and y? The first thing I'd do is I'd find the marginal distributions of x and y, and the reason is because that lets us find the expected values of x and y, right? The formula for covariance is the expected value of x times y minus the expected value of x times the expected value of y. So that's our second term, and we can get our first term by first calculating our x times y values right here. So what this means is 1 times 1 is equal to 1. And then we can give it a correlating probability, right? So let's say we wanted the probability x of y is equal to 2. Well, we look at every single possibility. We know that it's 2 when it's 1 times 2, and then it's 2 when it's 2 times 1. We add these two probabilities together, and then we get f of xy for 2 is 0.09 plus 0.16. Whoop. And that's 0.25. So that's essentially how you find the probability of each xy value. I've done it all here for you. You just add up all of the probabilities for 0 to get the probability that xy is equal to 0. You can do the same for 1, 2, and 4. Now, what that means is we can calculate e of xy, and that gives us 1.22. Now we can use that to find the covariance, which is e of xy minus e of x times e of y. So that's 1.22 minus e of x, which is 1.04, times 1, which is e of y. And that's 0.18. And that gives us the covariance. And since it's so small, we'd say most likely x and y, even though they're not independent, they don't exactly, affect each other based on their growth rates. And the last thing for bivariate is correlation. What is correlation? It's just a measure of given two random variables and having them be maybe plotted out as points, where each point represents the y value you get, as well as the x value you get from the two random variables. If these variables end up forming a line in the positive gradient, that gives us a correlation of 1. If it's a line in the negative gradient, that's a correlation of -1. And how closely it forms a line gets us how big or how small our correlation is. And a correlation of 0 means that the data points don't make a line at all. So, we're up to transformations. What is a transformation? I didn't render for some reason, but this should say the min of z1, z2, and so on until zn. So the transformation is essentially just taking a single or multiple distributions and then putting them through a function, right? A transformation is just a function that you put it through. In this case, we're taking a couple different distributions, z1 to zn, and then we're putting it through the min function, right? We're taking the minimum of them. So this is what we might do if we have a non-monotonic transformation. We'll talk about what monotonic means, but for now, if we have a non-monotonic transformation, a good strategy is that we first look at our capital F of x, right? And the reason we look at the capital F of x is because we can relate it to probability, and then we can work out some equations that let us finally get our distribution. So in this case, our question says we have zi, where I is the values from 1 to all the way to n, where they are IID. This means independent, individually distributed. Sorry, whoops, no, not identical. It means identically. So what that means is they all follow the same distribution and they're all independent. So z1 to zn are exponential distributions of 1. And we want to find the distribution of yn, which is the minimum of all of these. So for the minimum specifically, we generally use the fact that yn is less than or equal to all of zi, and if we translate this into our capital F of x, we see that f of yn is equivalent to the probability of yn, which is less than our value y. This isn't actually helpful for us because we want to use the fact that yn is a lower bound, right? So in this case, we have 1 minus y, and then we flip the sign, and that lets y be a lower bound. So what we can do is we can use the fact that since y is less than yn, which is less than or equal to zi, y is less than or equal to zi. Sorry, y is less than zi. So that's what we have here. Y is less than z1, y is less than z2, all the way to y is less than z3. Sorry, zn. Why is this important? Well, we can use the fact that it's independent, right? If it's independent, that means the probability of each z1, z2, all the way to zn are not affecting each other, which is why this is actually equivalent to the product of the probability with zi greater than y. And then what we find is that this is equivalent to 1 minus zi being less than y. And this is actually just 1 minus f of z given y. And that's how we make the transformation here. Except the thing is, we know what the capital F of z is, right? Z is the exponential distribution with parameter 1, and we know that this correlates with an f of z 1 minus e to the minus y. What this lets us do is we can cancel the 1's, and we get left with e to the minus y all the way with power of n, and that gets us our term right here. So in the end, our f of yn is 1 minus e to the minus ny. And if we differentiate, we can get our probability density function, which is n times e to the minus ny. So that's usually the process for non-monotonic distributions, right? We essentially just find the capital F, and what that allows us to do is it allows us to differentiate. Another example of the capital F you might have seen is, I think before there was a transformation of y, which is equal to z squared. In that case, it's not monotonic, so they were able to get a specific f of y and then turn it into something based on f of z's, and then turn that into some function which you can differentiate to get our probability density function. So here's an example from 2018 midterm question 4. We have x, which is a uniform distribution from 0 to 1, and we have minus log x as our transformation. So what's special about minus log x? It's what we call monotonic. But what is monotonic? It just means always increasing, always decreasing. That's pretty much it. It's either always increasing or always decreasing. So things like cubics, lines, negative gradient lines, right? Maybe a tan. Maybe it's a tan inverse, maybe it's an exponential, and so on, right? Logs, all of that. Since they're all monotonic, we can use this formula right here. But why do we need it to be monotonic? Well, this formula has y be equal to some function of h of x, right? But since we originally start with f of x for some x, we need to be able to transform this x into a y, and the way we do this is we use the fact that x is equal to h of inverse y. But this is only true if the inverse exists. And when does the inverse exist? When it's 1 to 1. So that usually means always increasing or always decreasing, which is why if the transformation is monotonic, we can use this formula, which is essentially replacing all of the x's with y's, and then we have a scaling factor, which just makes sure that the properties of a PDF exist still, right? Such as the things that are like having all of the sum of all probabilities be equal to 1, and having all of the probabilities be positive. So, what do we notice here? We have a h of x, and that's equal to minus log x. This is a log, and so this is clearly monotonic. That means we can first take our h of x and let it equal to v. The reason it's v is I think there used to be a part 3 of this question, but then I removed it just for time's sake. And that used a y, so I didn't use y here. But essentially, we have v, which is equal to minus log x. And what we can do is we can, since it's monotonic, find the inverse, where we have x is equal to e to the minus v. And then what we can do is we can differentiate this with respect to v, and that gets us e to the minus v, and then a minus in front, right? So we have a transformation here. H is monotonic, and what we do is we take our f of x, we replace the x with our function of v, and then we multiply it by the absolute value of our transformed derivative, which is e to the minus v. We know that e is always positive, so we don't need the absolute values. And then we know that this is a uniform distribution from 0 to 1, so f of x is actually always equal to 1, right? So 1 times e to the minus v is e to the minus v. And what do we realize? E to the minus v is actually just the exponential distribution where the parameter is 1. So that's how we find out that v, which is equal to minus log x, is equivalent to the exponential distribution with parameter 1. So here's our second question. Instead of having one variable be transformed, this actually adds up two different variables, specifically x1 and x2, which are exponential with parameter lambda. So how do we do this? Well, a common way is using moment generating functions. We know that the moment generating function of x plus y is equal to the moment generating function of x times the moment generating function of y. Why is this useful? Well, the reason is because every moment generating function is unique to the specific distribution. So that means, for example, the distribution that has the moment generating function of a normal has to be a normal. And the beta's moment generating function always belongs to a beta distribution, right? So in this case, for something like showing that the sum is equivalent to an already known distribution, it's very useful to use moment generating functions. So the first thing we do is we find out that the moment generating function for x1 and x2 are 1 on 1 minus lambda u. We know that the moment generating function of x1 plus x2 is just the MGF of x1 times the MGF of x2. So we just square it, and we see, based on our table, this is actually the moment generating function of gamma 2 comma lambda. And since we know that MGFs are unique to the distribution, we can say x1 plus x2 is actually equivalent to gamma 2 lambda. So we now have another sum. In this case, it is 2u plus v. I don't recommend using the moment generating function here because this only works specifically since we know what the MGF of a gamma looks like, right? But if we don't know the MGF based off the table, then it's really hard to tell what the actual function is. So in this case, we use a special tool. It's called a convolution. Essentially, if we want to find the PDF of x plus y, where x and y are distributions, we can use this fancy integral right here, where we integrate every possible y value with f of x, where the x value is z minus y, and then we multiply it by f of y, where we use the value y. This is with respect to dy, and that gets us an f of z of z. So, in this case, you might be saying, hey, this isn't two different distributions, right? The u is actually multiplied by 2, so we can't use u. Instead, what we can do is, we know that 2u can be transformed into a single distribution, right? So first, we know that u and v are uniform 0 to 1 distributions. So using this and the fact that we have w, which is equal to 2u, and this is monotonic, we can use our formula before to be able to find f of w for some w. We know that this would be the derivative, which is going to be u, which is equal to w on 2, du on u is equal to a half, so the absolute value is still equal to a half, and that's where we get the half from. And we know that f of u is always just equal to 1, since it's a uniform from 0 to 1. So we get 1 times a half, and so our end result is a half. And we also know that since u ranges from 0 to 1, and we double that range, we get a range from 0 to 2. So, now that we've simplified 2u to a w, we get x is equal to w plus v, so we can use the convolution formula, which is f of x is equal to this integral right here, where we multiply f of w, where the input is x minus v, and f of v, where the input is v. So the first thing I need to note is, for the distribution x, we're summing up a distribution w, which has a range 0 to 2, and a distribution v, which has a range 0 to 1. So the total range for x is 0 to 3. Now, we know a couple facts. The first one is, f of w is equal to a half, but only if the input is between 0 and 1, because it's a uniform distribution from 0 to 2. And since v is a uniform from 0 to 1, if the input is in between 1 and 2, then our f of v is equal to 1. Our goal here is to find out when are both fw and fv equivalent to a value, which is not 0, right? Because in our convolution, what we're doing is we're taking these two values and then we're multiplying them together. That means if one of them is 0, then both of them are going to be, the total product is going to be 0. So what we do is we have the fact that x minus v ranges from 0 to 2, and that's the only time when fw is a half, and we have the range v, which is from 0 to 1, and that's the only time v is a 1. If we multiply these two together, obviously the product is a half, and our goal is, when is this product actually available? So the first thing that I noticed is, clearly, v is between 0 and 1, and our output is some function of x. So my goal is to find out ranges of x where the value is equal to a half. So the first thing we notice is that we want x minus v to be between 0 and 2. And we know that v is between 0 and 1, right? So this actually gives me a range. X has to be between 1 and 2. Why is that? Well, if x is greater than 2, then what happens is, for example, if x is equal to 2.5, what if v is, since it's between 0 and 1, it's a maybe 0.05. This means x is minus v is equal to 2.45. This is obviously greater than 2. It's outside of this range, so f of w doesn't exist. That means it's a 0, so the product is equal to 0. What if x is less than 1? The same thing happens, but on the opposite side. If x is less than 1, let's say x is equal to 0.6, and maybe v is equal to a 0.7, x minus v is equal to 0.1 minus, and this is outside of the range since x minus v has to be greater than a 0. So what that means is if an x is outside of this range, we can't guarantee that x minus v is within 0 and 2. Which means if x is in between 1 and 2, then we've essentially just shown that x minus v is between 0 and 2, right? Because if x is less than 2 but greater than 1, no matter what value v is, we can guarantee that it's x minus v is in this range. So that's essentially what we've shown. If x is between 1 and 2, then we know that the product exists. So when we take the convolution, which is fw times fv, we know that the product is a half. Then we also know that since we're with respect to v, and v ranges from 0 to 1, that's what our bounds of the integral are. We evaluate the integral, and we get f of x is a half, given that it is between 1 and 2. So what we notice is that x is between 0 and 3, so we know what happens between 1 and 2, but we don't know what happens between 0 and 1 and 2 and 3. So let's look at the case where x is less than 1 but greater than 0. The problem was that if v is greater than or equal to x, then x minus v is less than or equal to 0, right? So what that means is to prevent this, right, for the product to exist, we need x minus v to be greater than 0, and that gives us a bound x greater than v. So this actually acts as an upper bound for our v, right? Because our product only exists if the specific x value is greater than our v value, right? So what we realize is, of course, if v is greater than x, then fw doesn't exist. So if we bounded v by 0 and x, then we guarantee that v is less than x, but then we also need v to be greater than 0. So this gives us our new bounds, 0 to x, and we know that during this bound, the product does exist. So the product is a half, and we know that when we take this integral, we get a half times x. And this is f of x, which is a half if x is in the range 0 to 1. And then we can do this for the final region, which is 2 to 3. We know that for an x greater than 2, if x minus v is greater than or equal to 2, then fw would be 0, right? So we need to make sure that this is still true, where x minus v is less than 2, and that gives us the lower bound for v, which is x minus 2, which is less than v. So what this means is, if we make sure that v is less than 1, which is always true, but then v is also greater than x minus 2, then this product exists. So we integrate from x minus 2 to 1, and we evaluate the integral to get 3 on 2 minus x on 2. We combine all of these together, and we get an f of x value for 0 to 1, 1 to 2, and 2 to 3. And this is our PDF. So that was a bit of a long ride, but I think if you understand this, it's very helpful, as this is a bit tough, and obviously the convolution just doesn't just work, since there are a lot of conditions in making sure that the product exists. So here's the final question of the seminar. Essentially, we have u and v equal to some value, some function of x and y, but we're not turning for example, a sum of 2 into one variable, right? We're maintaining 2 variables, so we can't use the methods that we had before. This time we need the Jacobian. So if we have u equal to g1 and v equal to g2, we know that the joint density of v and u is equal to the joint density of x and y multiplied by the absolute value of the determinant of the Jacobian. The Jacobian, if you haven't seen it before, is dx on u. So what is x? X is just a function of x, which is in terms of u and v. So what we realize is, to use the Jacobian, we need to have x in terms of u and v, and then y in terms of u and v. Then we can take the diff of x with respect to u, diff of x with respect to v, then diff of y with respect to u, and diff of y with respect to v. So something useful about this is actually a third method for computing an x plus y, because what we could do is we can find the uv x plus y and y, which would get us f of x plus y, y, x plus y, y. But then we realize that we can find the marginal density function by integrating out the y, and that gets us the x plus y function by itself. So this is the final question. We have f of xy, which is equal to x times y. We have u, which is equal to 2x, and v, which is equal to y squared. The first thing we do is we take these, and then we have x and y transformed in terms of u and v, right? Then we see that, of course, this is a positive square root, and the reason is because v is positive, right? That's why you have a positive square root. Then we get the Jacobian. So we know that x with respect to u is a half, x with respect to v, since there's no v term, is 0, y with respect to u is a 0, since there's no u term, and y with respect to v is 1 on 2 root v. And then we can find the determinant by multiplying these two and minusing the multiple of these two to get 1 on 4 root v. Then what we've done is we've taken our x, we've replaced it with our function of x, taken our y, replaced it with our function of y, then multiplied it by the determinant to get our final value of u18. So that's the end of our seminar. We actually have the revision sheets for statistics and linear algebra, which is 2901 and 2601 up. So if you follow this QR code, you'll be able to get every single important formula and theorem for the course. Also remember, at the start of the talk, we did have a QR code for attendance. It'd be really helpful for us, since it actually does give us money, for you to be able to sign it. And then we'll have tomorrow from 3 to 5 a seminar for the second part of 2901 to 801. We'll be covering things like estimators and convergence and hypothesis testing, so stay tuned. All right, thanks.